So today we're going to learn about the strong principle of mathematical induction. So what we're going to do is we're going to be given a statement. We're going to call that statement S of n, and that statement's going to involve the integer n. And the first step to mathematical induction is to suppose that for some integer n naught, that S of n is true for that n naught. And n naught is going to be our smallest integer that satisfies our S of n. And after we've shown that that n naught is true for S of n, we're going to move on to our inductive step. And the inductive step, it says that whenever k is greater than or equal to n, and k is an arbitrary element in the natural numbers that satisfies S of n. So whenever k is greater than or equal to n naught, and S of n naught and S of n naught plus 1, all the way up to S of k are all true, then S of k plus 1 is true. And that's what we're trying to prove, that S of k plus 1 is true. And then we can say that by mathematical induction, S of n is true for every integer n that's greater than or equal to n naught. For example, using strong induction, prove that this statement is true for all n in the natural numbers where a sub 1 is 1 and a sub 2 is 3, and for all other a sub n, we have 2a sub n minus 1 minus a sub n minus 2 for n greater than or equal to 3. So the smallest element that we have in our n is going to be 3. And our S of n statement is this statement here, this a sub n equals 2n minus 1. And we're going to use all the other given information to prove that this statement is true whenever n is at least 3 or greater than 3. So first thing we need to do is do our base step. And again, our smallest n that satisfies our S of n statement is n equal to 3. So what we're going to do here is show that n equal to 3 satisfies the statement we're trying to prove, which is 2n minus 1. And so we have that here. We just plug in 3 where n was, and a sub 3 is equal to 2 times 3 minus 1, which is 5. And we've also plugged in 3 for n in our given assumption statement here and shown that that was also 5. So we've shown that when n equal to 3, which is our smallest n that satisfies our S of n, this statement holds. It's true. So now we move on to our inductive step. So we're going to assume that n is equal to k, meaning k is some integer. And we're going to assume that k is true whenever it is greater than or equal to 3. And so here we have our S of n written in the form of S of k. And we've also given S of k minus 1, and we're going to see how that's going to help us in the next step. So we need to show that a sub k plus 1 is equal to 2 times the quantity k plus 1 minus 1. And once we've shown this, we've proven that our statement S of n is true for all n in the natural numbers. So here's how we're going to show that a sub k plus 1 is true. Since we know that a sub n is equal to 2a sub n minus 1 minus a sub n minus 2, we can say the same thing is true for k, as you see here. And since we know that a sub k plus 1 is equal to 2a sub k minus a sub k minus 1. So if we wanted to calculate a sub k plus 1, we know that that's going to be 2 times a sub k, and as we saw here, a sub k is equal to 2k minus 1, so we plug that in here, minus a sub k minus 1. And again up here we calculated a sub k minus 1 to be 2k minus 3, which is here. And after we do a little bit of algebra, we see that we get 2k plus 1. And so, what we're trying to show is that a sub k plus 1 is equal to 2 times the quantity k plus 1 minus 1. So we've gotten down to where a sub k plus 1 is 2k plus 1. So what we're going to do in order to get this statement here to look like this here on the right-hand side is we're going to change 1 into a quantity 2 minus 1, what we've done here. So all we've done is we've changed the number, the integer 1, into a difference of two integers, 2 minus 1. So that when we do that so that we can take out a 2, factor out of 2 from the first two terms, and we get 2 times the quantity k plus 1 minus this 1 here. And when we do that, we've shown that a sub k plus 1 is in fact equal to 2 times the quantity k plus 1 minus 1. And since we've shown that a sub k plus 1 is true, we have shown by the strong principle of mathematical induction that a sub n is true for all n in the natural numbers. Thank you.